Hi, my name is Steve Bleile and I'm a welder. Both for its speed and ease of operation, wire feed has become the standard in the welding industry. And with the availability of smaller diameter wires and less expensive welding machines, semi-automatic wire feed processes are now common in smaller shops, on farms, ranches, and even in home shops. Today we're going to look at flux core arc welding. This process uses a continuous tubular wire that surrounds an inner core of flux. Compounds added to this flux determine the characteristics of the arc and weld buildup. During the weld, these compounds clean oxides from the surface of the metal, helping the molten puddle to flow out. They also lift oxygen, nitrogen, and other impurities from the molten filler metal, producing a clean weld deposit. As the molten flux cools, it forms a protective slag covering over the hot weld bead. Now, in any type of welding, the molten metal needs to be shielded so that it doesn't come in contact with oxygen and nitrogen in the surrounding air. Flux core arc welding shields the molten metal two different ways, depending on the type of flux core wire, self-shielded or gas shielded, and these really are like two different processes. With the self-shielding wires, the molten weld puddle is shielded by gases created from the burning flux. These wires typically require less voltage, can be used over a wide range of metal thicknesses, and deliver a moderate deposit rate. Self-shielded flux core wires provide a wire feed process that's relatively mobile and can be used outside of a shop for structural, general fabrication, and repair. Self-shielded flux core wires are extremely versatile, and for beginners, it's probably the easiest type of welding to learn and use. With gas-shielded flux core wires, the compounds in the flux do not produce the gases necessary to protect the molten metal from contacting the surrounding air, so an externally furnished shielding gas is needed. These wires generally require a higher voltage, are considered most efficient on thicker metals, and provide high deposit rates. Because of the external shielding gas, these wires are used inside of a shop or some confined area for heavy fabrication and equipment repair. Both self-shielding and gas shielding wires have the potential to produce strong welds. There are differences between the two, both in setup and welding techniques. So let's start with self-shielded flux core arc welding. Self-shielded flux core wires were originally developed as an alternative to shielded metal arc welding, which is stick rod. With higher deposit rates, wire feed is more efficient. It's also easier to use, especially for beginners. In electric arc welding, the distance between the electrode and the metal, called the arc gap, is extremely important. Any change in the length of the arc will affect the amount of heat at the weld. With the wire feed processes, when the voltage and wire speed are set properly, the welding machine automatically maintains a uniform arc, even with slight variations in the position of the wire feed gun. You can run a weld bead the very first time you pull the trigger, but there is a little more to joining metal than just squirting wire. While the equipment does feed wire and maintain the arc, the welder still needs to control the position of the wire feed gun, the direction of travel, and the travel speed. There's also metal preparation and joint fit up. To use wire feed effectively requires the physical ability to control the wire feed gun, along with a basic understanding of the equipment and welding wires. A standard setup for the self-shielded flux core wires consists of a power source, a wire feed unit, the gun assembly, and a ground clamp. Smaller wire feed machines up to 200 amps will generally have the power source and wire feed unit combined. In the welding industry, where more powerful equipment is used, the wire feed unit may be separate from the power source. Wire feed welding machines may look different depending on the size and brand name, but they all do the same thing: feed wire and regulate current. So basically, they all have the same parts. Self-shielded flux core wires are typically used with a constant voltage direct current power source. Alternating current from the wall outlet is transformed into direct current to the electrode, which is the welding wire. The direction of flow, referred to as polarity, is determined by how the leads are connected to the terminals on the welding machine. For direct current electrode negative or DC minus, the lead to the wire feed gun is attached to the negative terminal and the ground clamp is attached to the positive. In theory, negative electrons flow from the welding wire, striking the base metal and forming the molten puddle quickly. Electrode negative is generally associated with lower voltage requirements and faster travel speeds. With direct current electrode positive, or DC+, the lead to the wire feed gun is attached to the positive terminal and the ground to the negative. Current flows from the metal to the wire. The molten weld puddle is formed by hot gases surrounding the arc. Electrode positive generally requires higher voltage settings and slower travel speeds. Self-shielded flux core wires are developed to run on a specific polarity. Some use electrode negative, others use electrode positive. It is important to set up the equipment for the polarity of the wire you're using. Wire feed also uses a constant voltage power source. This is different from a stick rod welding machine, which uses a constant current power source. During the weld, either the voltage or the amperage is always changing to maintain the arc. In wire feed welding, this mainly happens when the gun is held closer or further from the metal. With CV power sources, the voltage is set while the amperage varies to provide the current necessary to burn off the wire and maintain the arc. Constant voltage power sources stabilize quickly, maintaining a uniform arc length and allowing the drive rolls to feed the wire at a constant speed. In some situations, a constant current power source can be used, along with a voltage sensing wire feed unit. With the constant current power source, the amperage is set and remains fairly constant, while the voltage varies to maintain the arc. Special wire feeder units, often referred to as suitcase models, are designed to sense the voltage changes and vary the wire speed to maintain a uniform arc length. Voltage sensing wire feed units are typically used and work best with bigger welding machines and larger diameter wires. The wire feeder unit itself, either constant speed or voltage sensing, is fairly simple. There's a spindle to hold a roll of wire with a catch that's inserted into a hole in the back of the spool. The spring-loaded nut at the end of the spindle should be tightened just enough so the spool stops when the drive rolls stop and it doesn't continue from momentum. Drive rolls are designed to match the diameter of the wire indicated on the side of the rolls. The gun assembly contains a liner for the welding wire, a lead supplying current to the contact tip, and control wires attached to the gun trigger. At the end of the gun, there's an adapter, the contact tip, and a thread cover to protect the threads on the adapter. The contact tip is the last part of the welding machine's electrical system that energizes the wire. Tips are available with different size openings, and for good contact, you want the tip to match the diameter of the wire. To load the wire, mount the roll so the wire comes off relatively straight through a guide that keeps it centered in the groove on the drive rolls and into a steel liner inside the gun assembly. Before you close the drive rolls, make sure the wire is centered on the groove, then tighten just enough to keep the wire from slipping. Flux cord wires, which are relatively soft, can be deformed if the drive rolls are over-tightened. With the spool loaded, lower the hood, turn the machine on, straighten the lead up a little and pull the trigger. There is a very close tolerance between the opening in the contact tip and the wire diameter. You may want the contact tip removed until the wire is all the way through. Then reinstall it and you're ready to weld. Now, part of wire feed welding is maintaining the equipment to keep the wire feeding smoothly. It is very difficult to make a good weld when the wire is coming out in spurts. So let's look at a few things you need to pay attention to. Even though the wire looks clean, it does cause dust from the shop to gum up the liner. Installing a wiper with solvent made especially for welding wire helps keep everything operating smoothly. During the weld, small bits of hot metal called weld spatter fly out of the molten puddle. Depending on how clean the metal is and the position of the weld, globs of spatter may stick to the end of the contact tip. Occasionally, check the tip and scrape off any buildup. The wire can also burn back and stick at the tip, so it's a good idea to keep a few extra contact tips on hand. Wire feed machines are well built, and in most cases, feeding problems are not equipment failure, but rather some kind of contamination, either dust from the shop or weld spatter. Take the time to keep the machine clean and the wire feeding smoothly. Since the 1980s, when self-shielded flux core became popular, new wires have been developed to make this process more versatile and easier to use. Welding wires are classified by the properties of the finished weld. The E stands for electrode. The 7 indicates the weld metal has a 70,000 pound per square inch tensile strength, and tensile strength is the force it takes to pull it apart. The 1 indicates the wire can be used for welding in all positions: flat, horizontal, vertical, and overhead. A 0, like an E70T4, means the wire was designed for welding in the flat position only, or for a horizontal fillet. The T stands for tubular, indicating it is a cored wire. The last number refers to the characteristics of the arc and the properties of the weld. Depending on the type of flux, self-shielded wires can provide deep penetration or build up more weld. Some are limited to single pass only, others can be multi-pass for larger welds. Keep in mind, most wires were developed for industry, where welds are often made in the same position or specific mechanical properties are required. E70T3 and T10 are high-speed single-pass wires. E70T4 and T7 are multi-pass wires with high deposit rates. E70T6 and E71T8 are multi-pass, deep penetrating wires that meet the impact requirements for welding structural steel in seismic zones. For general purpose fabrication and repair in all positions, E71T-GS is often used with the lower voltage hobbyist type wire feed machines. These are recommended for a single pass weld with limits on the amount of weld buildup. E71T11, one of the most commonly used self-shielded wires, can be multi-passed, but is often limited to a weld buildup of 3/4 of an inch. With a smooth arc and spray metal transfer, E71T11 wires provide good weld fusion and are very easy to use in any welding position. This is the type of self-shielded wire we'll be using for our demonstrations. The diameter of the wire is selected for the amount of filler metal deposit, and in some cases, the size of the welding machine. In the welding industry, larger diameter wires provide maximum weld deposits in the flat position. Smaller wires are used for vertical and overhead welds, depending on the thickness of the metal. For general purpose welding, where you're working with different metal thicknesses in different welding positions, it's more of a compromise. 030 works well for the thinner gauge metals. 035 is used when the metal is mainly 1/4 of an inch or less, and both of these are commonly used with the smaller wire feed machines. 045 and larger wires are used for metal that's 1/4 of an inch and thicker. These are generalizations. If you can handle more metal, try a larger diameter wire. If you're doing a lot of vertical and overhead, you can always use a smaller wire for less weld deposit and better control. One last thing about flux core wires. These are classified by the finish weld, and the way manufacturers achieve this varies. Some wires, even in the same classification, may be easier to use than others. If you seem to be having a problem, you may want to try a different brand of wire. Okay, we've set this machine up with E71T11 all-position self-shielded flux core wire. Let's try some welding. Before you pull the trigger and throw sparks all over the place, cover yourself up. Wear some good gloves, a hat, and always wear safety glasses. Along with hot metal sparks flying around, slag or other impurities can pop from the surface of the metal as it's heating up or cooling. Make sure the lenses in your welding hood are clean. Use clear lenses to protect the shaded lens and check that everything is sealed so light doesn't leak around the edges inside the hood. Keep your work area clean and always have a fire extinguisher handy. Ideally, the ground clamp should be attached as close as possible to the weld. That's not always practical. Sometimes it's attached to the work table or further away on a structure, fabrication, or piece of equipment, but it is important to have a good clean ground. If the wire sputters at the beginning of the weld and the arc seems like it doesn't want to start, check the ground connection. Trim the wire 1/4 to 3/8 of an inch from the end of the contact tip. Get comfortable and use both hands on the wire feed gun so you can be as steady as possible. When you pull the trigger, circuits in the power source provide current to the wire and the drive rolls start to feed wire. When the wire touches the metal, the arc is started. The shape and amount of weld, along with penetration and weld fusion, are controlled by the distance the gun is held from the metal, the angle of the wire feed gun, the voltage and wire speed settings, and the travel speed. During the weld, you have to focus on the molten puddle, constantly analyzing how fluid it is, how the edges are flowing out, and watching the weld build up. Even though the welding machine does automatically maintain the arc length, the amount of wire that sticks out from the end of the contact tip to the metal, called electrode extension or wire stickout, will affect the amount of heat at the weld. CV power sources try to maintain a constant voltage, then provide the amperage necessary to burn off the wire. Longer electrode extensions allow the wire to preheat, reducing the amperage necessary to burn it off and reducing the heat at the weld. Shorter electrode extensions cause the amperage and heat to increase. Depending on the specific wire and wire diameter, the recommended electrode extension can range from 1/2 inch to 2.5 inches. For the smaller E71T11 self-shielded wire we're using, the wire stickout from the contact tip to the metal should be around 1/2 to 1 inch. For a smooth weld bead, you want to maintain a consistent wire stickout. While you want to avoid holding the gun closer, which can agitate the puddle, one of the unique characteristics of the self-shielded flux core wires is that you can back the gun away to fill gaps in poorly fit joints. You need to watch the puddle though, keeping it hot enough so the molten metal flows out on the sides. Under normal welding conditions, the gun can be held anywhere from nearly perpendicular to around a 15-degree angle back towards the weld. This is referred to as pulling the weld. When the gun is held more perpendicular, the arc stream is directed right onto the metal, causing the puddle to form and spread quickly. This can be used with a faster travel speed to limit penetration on thinner metal or for making smaller weld beads. As the gun is angled back towards the weld, some of the heat is taken off the metal. This allows a slower travel speed to build up more weld without overheating the base metal. You do want to avoid angling the gun too much. All the heat will be directed back onto the puddle, limiting penetration and possibly overheating the molten filler metal. Whether you're holding the gun up to spread the puddle or angling it to build weld, try to maintain a consistent gun angle for a smooth weld bead. For most welds, you can just move the gun in a straight line. A consistent wire stickout and travel speed will produce a uniform weld. You can also use a slight side-to-side motion, watching the outside edges to make sure the puddle is flowing out. As you gain experience, you can use more gun movement to deposit more metal, but avoid big wide gun movements that make the puddle more fluid and difficult to control. Either running straight or using a little gun movement, you want the wire and the arc directed at the leading edge of the molten puddle. This not only helps ensure good penetration and weld fusion, it keeps the molten slag back over the weld. This is very subtle, but where the wire hits the puddle makes a huge difference. If the wire is directed back further, the weld buildup limits the amount of heat that's transferred to the base metal, reducing penetration. Also, pushing the puddle in front of the wire increases the chances of trapping slag under the weld bead. Try to keep the wire towards the leading edge of the puddle, using the gun angle and direction of travel to keep the molten filler metal and slag behind the wire. The voltage and wire speed settings are the main control of the potential amount of heat and size of the weld. There are two parts to making the final adjustment. First, for penetration and weld fusion, the arc has to produce enough heat to melt the base metal while the filler wire is continuously added to the molten puddle. When the voltage and wire speed are set too low, the base metal does not get hot enough to melt, so the filler metal just stacks up on top. As the voltage and wire speed are increased, a molten pool forms, flowing out to the sides. The filler metal is fusing to the base metal, the weld is starting to penetrate, and you have control of the edges of the puddle. Increasing the voltage and wire speed spreads the molten puddle. The filler metal becomes more fluid and produces a smoother finished weld bead. Eventually, the puddle and base metal become too hot, making the weld buildup extremely fluid. This range from the point where the puddle is formed to the point where the filler metal is overheated is referred to as parameters. Typically, voltage and wire speed parameters are fairly wide, leaving the final settings up to the individual welder depending on metal thickness, weld position, and the level of skill. Once the amount of heat and weld deposit is determined, the second part of adjusting the voltage and wire speed is tuning the arc length to provide a stable transfer of filler metal into the molten puddle. This adjustment can be made on some practice metal, adjusting either the voltage or the wire speed, as long as the dial is a rheostat and infinitely adjustable. If the dial clicks into ranges, you cannot change it during the weld. Watch the tip of the wire, looking directly at the arc length. If the wire speed is too fast for the voltage, the wire will run into the puddle, kind of exploding and causing excessive weld spatter. If the wire speed is too slow, the arc length is increased, causing the puddle to widen and flattening the weld buildup. The voltage and wire speed should be tuned for a short arc length right above the surface of the metal. Experiment with the voltage and wire speed. Watch the arc length, the puddle, and examine the finished weld bead. Most welding machines provide a chart with recommended settings. As your welder skills improve, you can increase the voltage and wire speed for higher deposit rates, better penetration, and smoother weld beads. The travel speed, how fast you move the gun, also affects the amount of heat at the weld. If the travel speed is too fast, the metal doesn't have time to heat up. The weld bead will stack up on top with limited penetration and weld fusion. Traveling too slow will generally put the wire and the arc on the weld buildup, causing excessive filler metal deposit and making the puddle difficult to control. Watch the puddle. You need to travel slow enough to allow the molten pool to spread, and at the same time, fast enough to keep the filler metal from becoming excessive and overheating. Then maintain a travel speed that keeps the molten puddle the same size. That's about all there is to the fundamentals of welding with self-shielded flux core wires. Set the equipment up with the correct polarity. Have a good clean ground. Use both hands on the wire feed gun. Adjust the voltage and wire speed to allow the molten pool to spread out and tune for a short arc length. Maintain the recommended wire extension with the wire directed towards the front of the puddle. Use the gun angle and travel speed to control the amount of weld deposit, then travel at a speed that maintains a uniform weld puddle. So far, all the demonstrations have been in the flat position. For a horizontal, we'll be welding across. Angle the gun up a little and slightly back towards the weld bead. Watch the top side of the puddle and the weld buildup. Maintain the recommended wire extension. Travel slow enough to allow the puddle to flow out, but fast enough to keep the filler metal from sagging. If the weld buildup does sag, either the base metal or the filler metal is overheating. Try traveling a little faster and make sure you're not angling the gun too far back into the weld. Vertical welds are made either uphill or downhill, depending on a specific wire. Some all-position self-shielded wires, because of the type and amount of slag, are designed for uphill only in the vertical position. With the general purpose E71T11 wires, downhill can be used on thinner gauge metals to limit penetration. Angle the gun up slightly, using the force of the arc to help hold the puddle up. Either running straight or using a slight side-to-side motion, travel fast enough to stay ahead of the weld buildup. Watch the sides to make sure the puddle is flowing out and to keep the weld bead straight. Traveling downhill limits penetration and will produce a flatter weld bead. For heavier metal, where more weld buildup is required, E71T11 can be run uphill. Hold the gun nearly perpendicular to the metal. Either using a slight zigzag motion or running straight, travel fast enough to keep the weld buildup from spilling down. You may want to use a slightly lower voltage and wire speed, but not too low, as many problems are caused by running too cold as by running too hot. For welding uphill, it is important to have the voltage and wire speed tuned for a short arc length and to maintain a consistent wire extension. Watch the sides of the puddle and the filler metal buildup to keep the weld bead uniform. Overhead welds are just like flat welds. Hold the gun nearly perpendicular to the metal or even slightly angled back towards the weld. Maintain a uniform wire extension and travel speed, keeping the wire on the leading edge of the puddle. As long as you don't overheat the base metal or the weld puddle, the molten filler metal will stay right up there. The real challenge of welding overhead is finding a comfortable position so you have complete control of the wire feed gun. If the wire extension, gun angle, or travel speed varies, the amount of heat at the weld will not be constant, making the puddle more difficult to control. Find some way to be as steady as possible. While self-shielded wires are relatively simple to use, you do need to understand the molten weld puddle and develop the physical ability to control the wire feed gun. Practice and examine the finished weld. A uniform bead will come with experience, but the edges should be tied in nicely. If the bead stacks up, the voltage and wire speed may be set too low, the travel speed may be too fast, or the gun might be angled too far back into the weld. Excessive filler metal deposits are caused by too slow of a travel speed. Self-shielded flux core wires do produce weld spatter. The best you can do is to make sure the voltage and wire speed are tuned for a short arc length. Also, increasing the voltage and wire speed will help to reduce the size of the spatter. If you can handle the molten puddle, turn up the heat. When you're comfortable running weld beads, try practicing on some weld joints. While there are many variations, basically there are 4 types: butt joints, lap joints, T-joints, and corner joints. The first steps to making any type of weld joint are metal preparation and joint fit up. Clean any dirt, paint, or grease, and whenever possible, even the mill scale from the surface. When you cut the metal, keep the edges straight and square, and if you're fitting up with a gap, try to keep it uniform. You can avoid a lot of problems by taking the time to get the metal ready to weld. Butt joints are joining the edges of the metal, and this can be on plate, flat bar, angle iron, pipe, or square tubing. On thinner gauge metal, around 1/16 of an inch thick, butt the pieces together, trying for a perfect fit. Any gaps may cause the edges to meld away, ripping open a hole. If possible, try to position the thinner gauge metals to weld downhill. With downhill, you're welding away from the heated metal, limiting penetration and helping to avoid burning through. As the metal thickness increases, you want the amount of filler metal to equal the thickness of the base metal. The weld does need to penetrate deep, especially if there's any stress on the joint or you intend to grind the weld for a polished finish. For metal that's around 1/8 of an inch thick, try leaving a small gap, approximately 1/16 of an inch, and keep it uniform. If the pieces were fit up without a gap, take a grinder up on edge and grind a groove to allow for penetration. When the metal is around 3/16 of an inch and thicker, bevel the edges of the pieces being joined. Bevel should be around a 30-degree angle with a flat spot called a landing on the bottom. The landing helps prevent the bottom edges from melting away. Tack the pieces together with a uniform gap, then grind the edges of the tacks thin. The amount of gap depends on whether or not complete penetration is required. If 100% penetration is not necessary, use a narrowed gap. With the gun held more perpendicular, run the first pass deep in the joint, making sure the puddle flows out and ties in on the sides. For complete penetration, use a slightly wider gap. Start the arc and move to the front of the tack on the bottom edge of the bevel. Bring the wire across, slightly back on the puddle, to the edge of the bevel on the other side, then just back and forth, staying deep in the joint. Once the first pass is in, clean off the slag with a chipping hammer and wire brush. Anytime you weld in a bevel, you want the filler metal buildup uniform. If there's high spots from stopping and starting, use a grinder up on edge to even up the weld. Depending on the metal thickness, you may be able to finish in one more pass. With the gun angled and a slower travel speed, build up weld slightly wider than the bevel and above flush with the surface. For heavier metal, run as many beads as it takes. Clean the joint after each pass and overlap the edges of the weld beads to avoid trapping slag. On lap joints, where one piece overlaps the other, the weld is called a fillet. The goal is to melt and fuse the bottom corner, and the weld should come up and out a distance equal to the thickness of the metal, with the bead slightly crowned. There are two wire feed gun angles that you have to consider for fillet welds. The work angle in relation to the pieces of metal, and the drag angle, which is relative to the weld bead itself. The work angle controls the position of the weld in the joint, and the angle will vary depending on the thickness of the metal. On thin gauge metals, the top piece will heat up and melt faster than the bottom. Direct the wire and the heat onto the bottom piece, allowing the puddle to flow out and tie into the top. As the metal thickness increases, direct the wire into the bottom of the joint with the wire feed gun angle to help push the puddle up. The drag angle affects the shape of the weld bead. Holding the gun more perpendicular to the weld allows a faster travel speed and produces a flatter bead. With the gun angled slightly back towards the weld, a slower travel speed can be used to build up more weld. Avoid angling the gun too much. The heat of the arc will not be directed onto the base metal, limiting penetration. To melt and fuse the bottom corner, keep the wire towards the leading edge of the puddle. For more weld buildup on heavier metal, you can either increase the voltage and wire speed or stack overlapping weld beads to provide the required amount of weld deposit. A fillet weld is also used for T-joints, and this is similar to a lap weld. In the horizontal position, direct the wire at the bottom piece, right in the corner of the joint, with a gun angle to help push the puddle up. Maintain a uniform wire extension and travel speed for a smooth weld bead. As you gain experience, you can use a little gun movement to deposit more metal. Always keep the wire directed into the puddle and bring the wire back to the leading edge to ensure good penetration and stay ahead of the puddle. For an overhead fillet, angle the gun to push the puddle up. Hold the gun nearly perpendicular to the weld for a flatter bead or angled very slightly back to carry more metal. For vertical fillets, try welding downhill with E71 T11 on thin gauge metal to limit penetration. On heavier metal, run uphill, stacking overlapping weld beads. As you gain control, you can use some gun movement to deposit more metal on vertical up. For the first pass deep in the corner, hold the gun nearly perpendicular to the metal. Bring the wire out to the side, making sure the puddle flows out and ties in. Then move back into the corner and over to the other side. Pay attention to the wire extension, moving the gun into the corner to maintain a uniform wire stick out. If you just come across, the wire extension will increase in the center, then shorten on the sides. Try to maintain a consistent wire extension to keep the amount of heat uniform. If you need more weld deposit, you can overlap smaller beads or try running a weave bead. Starting on one side, let the puddle flow out. Move across to the other side, hesitating if necessary to let the puddle flow out, then cross back and forth, keeping the wire extension and travel speed uniform and the upward progression tight. Watch the sides to make sure the puddle is flowing out and to keep the weld bead straight. Weaving takes some practice, but will allow you to build up more weld in the vertical up position. Corner joints can be fit up several ways, depending on how you want the finished weld to look. One piece can be beveled to provide sufficient penetration. If the pieces were fit up without a bevel, use a grinder to groove the joint. For ornamental type projects, this type of fit up can be polished for a nice square corner. Corners can also be fit up by butting the inside edges of square cuts. Angle the gun right into the bottom and adjust the travel speed so the puddle spreads all the way to the top and the bottom. If you can't fill the corner with one pass, try running the first bead filling to the bottom edge, then making a second pass filling to the top. On heavier metal, stack as many beads as it takes. For ornamental projects, this can be polished for a round corner or ground flat for a beveled look. If you're concerned about the strength on any type of corner joint, you can run a fillet weld on the inside, but this will cause the pieces to draw in the direction of the fillet. Whenever possible, try to make the outside weld first. Whether you're fabricating with new metal or making repairs, always remember that every weld joint is made one weld bead at a time. Understand the characteristics of the specific welding wire you're using. Take the time to get the metal ready to weld. Set the voltage and wire speed high enough to allow the puddle to spread out, tuned together for a short arc length. Watch the edges of the puddle and the weld build up, then travel at a speed that maintains a uniform weld puddle. Maintain the recommended wire extension using the gun angle and travel speed to control the amount of filler metal deposit and the shape of the weld bead. Gas-shielded flux core arc welding is the main semi-automatic wire feed process used in the welding industry for heavy fabrication. High deposit rates and good weld fusion, along with ease of operation, also make this an excellent process for the in-shop repair of farm and construction equipment. Gas-shielded flux core wires require an externally furnished shielding gas that prevents oxygen and nitrogen in the surrounding air from coming in contact with both the filler metal as it's transferred from the tip of the wire and the molten weld puddle. In addition, compounds added to the flux and the welding wire, called deoxidizers, help remove surface oxides and other impurities from the weld puddle. As the molten flux cools, a slag covering is formed that continues to protect the hot weld bead from contacting the surrounding air. This combination of shielding gas, flux, deoxidizers, and the slag covering produces clean filler metal deposits, even on larger welds. Gas-shielded flux core uses the same type of wire feed unit and direct current constant voltage power source as the self-shielded wires. Because higher voltage and amperage is required, power sources typically range from 300 to 400 amps. Smaller machines, down to 200 amps, can be used, but are limited to the smaller diameter wires. The wire feed machine also contains a gas delivery system along with a shielding gas cylinder and flow meter. Either straight carbon dioxide or a blend of 75% argon and 25% CO2 is used with many of the gas-shielded wires. Straight carbon dioxide is less expensive and produces a high-energy arc stream that provides good penetration and weld fusion. CO2 is typically used in the welding industry with welding wires designed for the flat position. Because argon transfers current better, a 75-25 shielding gas allows a slightly lower voltage, resulting in a smoother arc and making the weld puddle easier to control. 75-25 is commonly used with the gas-shielded flux core wires designed for all-position welding. These are high-pressure bottles and can be filled to over 2,000 pounds per square inch. You need to protect this valve from getting damaged, so when the bottle's in use, it needs to be chained securely, and when it's not in use or you intend to move the bottle, use the protective valve cover, even when the bottle is empty. The flow meter regulates the amount of gas flow measured in cubic feet per hour. There are different styles of flow meters, with a high pressure gauge indicating the pressure inside the bottle and the other gauge used to adjust the flow of gas. The gas delivery system includes a solenoid inside the machine that allows the gas to flow when the wire feed gun trigger is pulled, and a hose inside the gun assembly. At the end of the gun, you have an insulator, an adapter, sometimes called a diffuser, the contact tip, and the nozzle. Contact tips come with different size openings to match the diameter of the welding wire and in different lengths. For gas-shielded flux core welding, the contact tip should be recessed approximately ½ an inch from the end of the nozzle. The gas flowing around the tip helps keep it from overheating. During the weld, spatter flying out of the molten puddle will collect on the inside of the nozzle, possibly disrupting the flow of gas. Check this occasionally and clean out any buildup of weld spatter. Gas-shielded welding wires are classified by the chemical and mechanical properties of the finished weld. E70T1 and E71T1 are the most common wires for welding on carbon steel. Both run on DC electrode positive and have a 70,000 pound per square inch tensile strength, indicated by the 7. The 0 in E70T1 indicates wires designed for welding in the flat position and for horizontal fillets. With the CO2 shielding gas, these are typically used in the welding industry for extremely high deposit rates. The 1 in E71T1 indicates an all-position welding wire and is commonly used both in the industry and smaller shops with a 75-25 gas blend for general purpose fabrication and repair. Every manufacturer does have several choices of wires in the T1 classification. Some wires have more deoxidizers for welding on metal that's slightly rusted, or they're designed to run with a specific shielding gas. The welding wire and wire diameter is selected for the type and conditions of the project you're working on. To load the wire, trim the wire cleanly, avoiding any bends or burrs. Before you close the drive rolls, make sure the wire is centered on the groove, then tighten just enough to keep the wire from slipping. With the spool loaded, close the hood, turn the machine on, and pull the trigger. When the wire is all the way through, install the contact tip and the nozzle. To open the shielding gas bottle and adjust the flow meter, crack the valve slowly to avoid hammering the internal diaphragms in the flow meter, then open the valve all the way. High pressure bottles have two seats, one to close the bottle and the other to seal the valve stem when the bottle is open. So open the valve all the way. Regardless of which type of flow meter you're using, you'll get a more accurate reading with the gas flowing, so pull the trigger on the wire feed gun to make the adjustment. The gas flow setting depends on the size of the weld puddle and the surrounding conditions. The idea is to use the minimum amount necessary to shield the weld puddle. If there's not enough coverage, voids called porosity can form in the weld bead. Too much flow can have a cooling effect and create turbulence, making the weld puddle more difficult to control. Generally, 30 to 40 cubic feet per hour is sufficient for the smaller wires, and 40 to 60 cubic feet will provide coverage for the larger wires. Some industrial machines will have a spool and purge button. The spool button activates the drive rolls to feed wire without opening the shielding gas solenoid. This is handy for loading wire or working on feeding problems. The purge button allows the gas to flow without activating the drive rolls and can be used to adjust the flow meter without running out excessive amounts of wire. Okay, we've loaded some E71T1 all-position welding wire with a 75-25 shielding gas. And even though this type of welding wire runs hot, produces big welds with high deposit rates, gas-shielded flux core arc welding is very simple. Just like every other semi-automatic wire feed process, the wire extension, gun angle, direction of travel, and the voltage and wire speed all work together to control the amount and shape of the weld deposit. E71T1 flux core wires have a spray-type metal transfer. Electrical energy breaks the filler wire into small droplets that are sprayed across the arc stream. If the voltage and wire speed are set too low, there is not enough energy to break up the wire. The filler metal is transferred in globs that can escape the arc stream, causing excessive weld spatter. As the voltage and wire speed are increased, the arc smooths out and the molten puddle becomes more controllable. Recommended voltage and wire speed parameters are available from the manufacturers of the wire, but the final settings are determined by the metal thickness, weld position, and level of welder's skill. In the flat position, high voltage and wire speeds can be used to produce more weld deposit. For vertical and overhead, slightly lower settings keep the amount of heat and filler metal deposit more controllable. The voltage and wire speed also need to be tuned together. In the welding industry, the wire speed is usually adjusted to provide the quantity of weld required. The voltage, which controls the length of the arc, is then adjusted for a short arc length. Make some practice welds looking directly at the tip of the wire. If the voltage is set too low, the wire will appear to run into the puddle, causing excessive weld spatter. When the voltage is set too high for the wire speed, the arc length increases, making the molten puddle extremely fluid and difficult to control. Tune the voltage for a short arc length just above the surface of the metal. Having the voltage and wire speed adjusted together helps reduce the amount of weld spatter and makes a big difference in having control of the molten puddle, especially when you're welding in the vertical and overhead positions. For E71T1 wires, the recommended electrode extension, which is the distance from the end of the contact tip to the metal, is approximately 3/4 of an inch to 1 1/4 inches. With gas-shielded flux core arc welding, the contact tip should be recessed about 1/2 inch. This not only helps keep the tip cooler, it also places the nozzle closer to the metal, ensuring good shielding gas coverage while maintaining the recommended electrode extension. During the weld, try to maintain a consistent wire extension. Even though the welding machine will maintain the arc, varying the position of the wire feed gun will affect the amount of heat at the weld. With a constant voltage type power source, longer electrode extensions allow the wire to preheat, reducing the amperage necessary to burn off the wire and cooling down the weld puddle. A shorter electrode extension increases the amperage, agitating the molten puddle. For a uniform penetration and a smooth weld bead, maintain a constant wire extension. In the flat position, where you can handle more metal, use the upper end of the voltage and wire speed parameters. With the gun angled anywhere from straight up and down to about 15 degrees, pull the weld, making sure the molten slag and filler metal stay behind the wire. Watch the puddle, adjusting the travel speed to allow the molten metal to flow out on the sides, but fast enough to avoid excessive filler metal buildup. Because of the high amount of heat and filler metal deposit, try running straight without any gun movement. Keep the wire directed towards the leading edge of the puddle. If you think you can handle more metal, try increasing the voltage and wire speed. For the vertical weld position, E71T1 is run uphill only. Set the voltage and wire speed in the lower range of the weld parameters. With the wire feed gun nearly perpendicular to the metal, maybe angled up slightly, try traveling straight up without any gun movement. Maintain a constant wire extension to keep the amount of heat at the weld uniform. Watch the edges and the filler metal deposit, traveling up fast enough to keep the buildup from spilling down. If you have problems with uphill, make sure the voltage and wire speed are set high enough and tuned for a short arc length. Horizontals are welding across. With the voltage and wire speed set in the middle of the welding parameters, angle the gun up slightly. Try starting with the gun nearly perpendicular to the weld. As you gain experience and control, you can angle the gun slightly back into the weld to carry more metal. Watch the top of the puddle to keep the weld straight, and watch the weld deposit, traveling fast enough to keep the buildup from sagging. If the weld deposit does sag, make sure you're not angling the gun back into the weld too much, then try increasing the travel speed to keep the base metal and weld puddle cooler. Overhead welds are just like flat welds. The real challenge is finding a comfortable position so you have complete control of the wire feed gun. Try holding the gun nearly straight up and down, maybe angled very slightly back towards the weld. When you maintain the recommended wire extension and a uniform travel speed, the molten filler metal will stay right up there. On an overhead, you need to keep the base metal and weld puddle from overheating. If the voltage is not adjusted for a short arc length or the gun is angled back into the weld too much, the molten puddle will become so fluid it may drip. Also, if the travel speed is too slow, the base metal can overheat, which causes the puddle to become more fluid and difficult to control. Hold the gun nearly straight up and down. Keep the wire towards the front of the puddle and watch the weld build up, traveling fast enough to keep it from becoming too fluid. Regardless of the weld position, flat, vertical, horizontal, or overhead, set the voltage and wire speed high enough for a spray transfer. Tune the voltage for a short arc length. Maintain the recommended wire extension and provide a sufficient amount of shielding gas to cover the molten puddle. Problems arise when you try to weld outside of these parameters. Excessive weld spatter can be caused by the voltage and wire speed set too low, or the voltage is set too low for the wire speed, allowing the wire to run into the puddle. Porosity, which is voids in the weld from gas pockets, is generally caused by impurities like dirt, rust, or paint on the surface of the metal. Porosity also results from losing the shielding gas coverage, either not having enough flow or holding the wire feed gun too far away from the metal. Worm tracks are lines created by gases trapped on top of the weld bead as the flux solidifies. These are typically caused by using too high of a voltage and wire speed, along with traveling too fast. They can also be caused from an incorrect wire extension. Take the time to practice. Experiment with the voltage and wire speed settings. learn to control the amount of weld deposit, and develop the skills to maintain a uniform wire extension and travel speed. Gas shielded flux core is typically used on heavier metal for structural and equipment fabrication or repair. Metal preparation and joint fit up are extremely important. Clean any contamination like dirt, rust, paint, or grease from the surface of the metal, even the mill scale, whenever possible. Because of the amount of heat and weld deposit, gas shielded flux core does not work well for filling gaps. Keep the edges of the metal straight and avoid excessive gaps during fit up. On butt joints, metal preparation and fit up depend on whether partial or complete joint penetration is required. 100% penetration is not necessary. Prepare the bevels with a small landing to help prevent the bottom edges from melting away. Tack the pieces together with a 1/16 to 3/32 gap. Holding the gun a little more perpendicular to the metal and the wire directed towards the leading edge of the puddle, put the first pass deep in the joint, making sure the puddle flows out and ties into the sides of the bevel. When complete penetration is required, you can use the same type of fit up, running the first pass as deep as possible, then grinding or gouging the backside to clean metal and running a weld bead above flush. A V-bevel with a backup bar can also be used for complete penetration welds. Prepare the bevels with a feathered edge. Grind the mill scale off the backup bar and fit the pieces with a 3/16 to 1/4 inch gap, either staggering tacks on the backside or tacking in the bevel. If you do tack in the bevel, grind the starts and stops thin. For the first pass, keep the wire in the center, making sure the puddle stays behind the wire and flows out, tying in on the sides. If you direct the wire onto the sides of the bevel, the filler metal can actually float across, not fusing the bottom edge of the bevel. After the first pass, run as many beads as it takes to fill and cap slightly wider than the bevel and above flush with the surface. On heavier metal, plan the weld, using the travel speed and gun angle to control the amount of weld deposit. Fill slightly below flush, leaving the top corners of the bevel as a guide for the final passes. To cap a wide bevel, overlap weld beads side by side. With the wire feed gun angled a little to build up weld, use the edge of the bevel to keep the bead straight. Then use the inside edge as a guide, adjusting the travel speed to allow the puddle to flow almost to the middle of the first pass. If the final pass needs to be smaller, hold the gun more perpendicular and increase the travel speed for a narrower bead. In any welding position, flat, horizontal, vertical, or overhead, running hot and straight, stacking as many beads as it takes is the simplest way to fill and cap heavier metal. A fillet weld is used on both lap joints and T-joints, and the technique for both is very similar. Direct the wire into the corner, slightly towards the bottom piece. The work angle determines the position of the fillet in the joint. Angle the wire feed gun to help push the puddle up. Holding the gun more perpendicular to the weld will produce a flatter bead, and when necessary, allow you to travel faster for less weld deposit. Angling the gun slightly back will build up more weld and produce a slightly crowned weld bead. Keep the wire towards the front of the puddle for good weld fusion in the bottom corner. On heavier metal, stack up overlapping beads to build up the required amount of weld. Fillet welds are pretty easy with gas shielded flux core. Just make sure the puddle and slag stay back behind the wire. If molten metal floats in front of the wire and you push the puddle, there is a good chance the bottom corner will not be fused. Corner joints can be fit up with one-piece bevels or by butting the inside edges of square cuts. On thinner metals, open the bevel up so you can control the puddle in the bottom of the joint. On heavier metals, a smaller bevel is often used to reduce the amount of weld deposit and time it takes to complete the joint. The beveled side is going to heat up quicker. Angle the gun as necessary to allow the puddle to flow out and tie into both pieces. On an outside corner, because of the amount of heat and filler metal deposit, the weld will try to sag. For thinner metals, holding the gun more perpendicular to the weld along with a faster travel speed will help keep the base metal and molten puddle cooler. As the metal thickness increases, it may take two passes, the first filling to the bottom corner, the second filling to the top. On heavy metal, Bring the filler deposit up and out evenly, leaving a little of the edges for the final weld. Every type of weld joint in any position is made one weld bead at a time, and it always comes back to controlling the wire extension, gun angle, and travel speed. Even though it's hot, with a considerable amount of weld deposit, gas shielded flux core is not complicated. Don't be bashful. Turn up the heat, run straight, and keep it simple. Well, I hope I've given you an idea about flux core arc welding. With moderate deposit rates, the self-shielded wires are used for structural, fabrication, and repair outside the shop. They're also an excellent type of wire for the smaller wire feed machines. Gas shielded wires with higher deposit rates are used inside the shop for heavy fabrication and repair. Choose the type of wire for the projects you're working on and understand the characteristics and parameters of the specific wire you're using. Watch the puddle and practice developing the skills to control a wire feed gun and figuring out just what works for you. Take your time, have fun with this, and above all else, work safely.